Have you ever tried to picture endless and felt your mind run out of room? Start small and count steps on a staircase that never reaches a landing. Then zoom out and measure space that keeps making more space. Infinity isn't a single thing. It's a family of ideas, sizes that can't be finished, processes that never stop, sets that outgrow our ability to list them. It shows up in simple fractions, in the night sky, and in the limits that shape physics and math. Stay with the edge where numbers stretch and meaning holds. Listen for the places where the infinite is useful and where it misleads. If this kind of quiet exploration suits you, a like and subscribe helps others find it. Settle in. Let's follow the trail as far as thought can go. What does it mean for something to have no end? The word infinity sounds plain, yet when you look closely, it becomes one of the oddest ideas we use. It shows up in simple steps that never finish, and in the thought that space might stretch forever. It sits between imagination and science, useful and unsettling at the same time. People have asked about it for as long as they have watched the night sky. Are there edges out there? Or do the stars keep going without a wall or a final line? Early thinkers tried to fit this idea to motion, to space, and to time. Later, mathematics gave it symbols and rules. Physics still meets it at the edges of equations, where numbers blow up, but nature does not. Infinity touches how we measure space, how we count time, how we describe energy, and how we imagine possible worlds. It does not stay in one box. It helps, and it hinders. Without infinity, formulas would be smaller. With it, our models reach farther. The topic has many faces, from old puzzles to current research, from the tiny to the vast. Some parts delight, some parts confuse, and some give a steady sense of scale. Infinity is not an object you can hold or even picture cleanly. It shapes how you think. Let it unfold slowly, like a horizon in a clear sky. Ask what it means, and you begin a path that does not end. The idea seems simple when you say it, and then turns slippery when you try to reason through it. People have looked outward to the stars and inward to their thoughts and found the same question waiting. Can something truly be without limit? Long before modern science, the question took shape in argument and story. The Greeks often pushed ideas to the edge. A thinker named Zeno, from the 5th century BCE, made a set of paradoxes that still get attention. He did not give comfort, he gave problems. His goal was to test our hidden assumptions about space, time, and motion. One of his famous puzzles goes like this. To cross a room, you first go halfway. Then, you go half of what remains. Then, half of what is left after that. And on and on. If that cut continues forever, how do you ever reach the far wall? The steps never end. In real life, you do reach the wall. The paradox, though, points at attention. Space seems to allow endless division. Motion seems to finish in a finite time. How do those facts live together? Another puzzle features Achilles, the fast runner, and a tortoise. Give the tortoise a small head start. By the time Achilles reaches the tortoise's starting point, the tortoise has moved ahead a little. When Achilles reaches that new point, the tortoise has moved again. The chase seems endless. We know a sprinter will pass a tortoise. Zeno's point was different. Even simple motion hides an infinite chain if you analyze it step by step. Other cultures met infinity in their own ways. In India, the idea of vast cycles of time, kalpas, described a universe that is created, dissolved, and created again in spans beyond counting. The picture is not about a single start or finish, but about a rhythm that dwarfs a human life. In Chinese thought, Taoist writing describes the Tao as boundless and without a fixed start or end, a principle that underlies things and resists full naming. That is not infinity as a number line running off to the right. It is infinity as a quality of existence, an unfolding that does not close. In the ancient Near East and along the Nile, careful sky watchers met a different kind of endlessness. The dome of stars looked without edge. The river returned. The seasons cycled. Day followed night without fail. Infinity was not a proof on a board. It was a pattern lived with, year after year. A common question came up again and again. Does the universe have a boundary? Imagine a wall at the edge of everything. What is beyond it? If there is something beyond, then the wall is not the end. If there is truly nothing beyond, how can nothing have an edge? The mind finds both options hard to hold. An end feels strange. No end at all feels strange. Infinity lives in that uneasy space between the two. Early mathematics also met this tension. Greek thinkers drew a line between potential infinity and actual infinity. Potential infinity means a process that can continue without stopping. You can keep adding one to a number. You can keep dividing a distance into halves. Actual infinity would be a completed whole, an infinite set that exists as one finished thing. Aristotle argued that actual infinity does not exist in the natural world. To him, infinity was always a process, never a completed object. The distinction still matters. When you count, you never arrive at a final infinity. You just keep going. Infinity here is not a destination. It is the road that does not run out. Religious language also used infinity to describe what is beyond us. A divine being might be called eternal or without limit, beyond time and decay. Infinity became a way to point at what does not wear down, while human life clearly does. Across cultures and ages, people kept circling the same theme. The endless has a pull. It challenges and it clarifies. It widens the frame. Numbers hide infinity in plain sight. Start counting. 1, 2, 3, 4, 5. There is no largest whole number. However far you go, another number waits. Children learn this quickly. They ask what comes after the biggest number. The honest answer is that there is no biggest. Think of a path of stepping stones across a river with no far bank. You can keep moving, but there is never a final stone to stand on and declare this is infinity. That is potential infinity again. The process has no end, but there is no single point you can grab and say this is the infinite. Now look at even and odd numbers. Common sense might say the full set of whole numbers is bigger than just the evens, because the evens are only part of the list. Infinity does not behave that way. You can match each whole number to one even number, 1 with 2, 2 with 4, 3 with 6, and so on. This perfect pairing shows that the evens and the full set of whole numbers have the same size in the sense that matters for infinite sets. The same is true for the odds, the square numbers, or the prime numbers. All go on without end. All can be paired one-to-one with the whole numbers. Removing an infinite part does not make the rest smaller in the usual way. This odd behavior troubled thinkers for many centuries. In the 1800s, a German mathematician named Georg Cantor decided to face it directly. Instead of avoiding infinity, he studied it. He found that not all infinities have the same size. For most people, infinity just means endless, a single blur. Cantor showed that there are levels. Some infinities are strictly larger than others. He started with the whole numbers 1, 2, 3, and so on. This is called a countable infinity. Countable means you can list the items, matching each item to a place in the list, even if the list never ends. Fractions seem trickier. Between any two whole numbers, there are infinitely many fractions. Still, Cantor proved that fractions are countable, with a clever way of listing them, often called a diagonal listing. You can arrange all positive fractions so that each appears at some step and none are missed. That result is surprising but true. Then he took the next step. Look at the real numbers, which include whole numbers, fractions, and also decimals that do not repeat or end, like the square root of 2. Cantor proved that the real numbers cannot be listed. No matter how you try to arrange them in a line, a new number can be built that is not on your list. This is Cantor's diagonal argument in another form. The conclusion is strong. The infinity of real numbers is larger than the infinity of whole numbers. He used the word cardinality to describe the size of a set. The real numbers have a greater cardinality than the whole numbers. He called their size the continuum. This was more than a neat trick. It changed the base of modern set theory, which supports much of today's math. Not everyone liked Cantor's findings. Some argued the results were too abstract or even dangerous to clear thinking. Over time, the work held firm and became central. Once you accept that infinities can differ in size, questions open up. Are there sizes of infinity between the size of the whole numbers and the size of the real numbers? The famous continuum hypothesis asks that question. Its status is special. Within the standard rules of set theory, it can be assumed true or assumed false without causing a contradiction. That tells you how unusual infinity is. It pushes the limits of what our basic rules can settle. Another helpful picture comes from David Hilbert's Infinite Hotel. Imagine a hotel with rooms numbered 1, 2, 3, and so on, all occupied. A new guest arrives. You can still fit them in by moving the guest in room 1 to room 2, room 2 to room 3, and so forth. Room 1 opens up. Now, imagine an entire bus with countably many new guests. Move each current guest from room N to room 2 newtons, doubling every room number. All the odd-numbered rooms become free, and there are infinitely many of those. The hotel can accept the whole bus. If several buses arrive, you can repeat the trick in other patterns. The point is not about real hotels. It is about how infinite sets behave under shifts and pairings. The reverse case is just as strange. If guests in every second room check out, there are still infinitely many guests left. If everyone but the guest in room 1 leaves, you still have infinitely many guests left, depending on how you do the leaving. Subtracting infinity from infinity does not work like subtracting 10 from 10. The result depends on the exact rule you use. That is why care is needed when working with infinite sets and sums. These ideas are not only puzzles, they are tools that support key parts of math and science. Calculus uses infinity all the time, but in a controlled way. To find the slope of a curve at a point, you look at the change in height over a tiny change in horizontal distance, and you let that tiny change shrink without bound. You never reach zero distance. You study the limit as the distance tends to zero. A limit is a way to capture the effect of an infinite process with a precise finite value. Infinite sums can also behave well. Add 1 2 plus 1 4 plus 1 8 plus 1 1 6 and keep going. The total approaches 1. The steps never end, yet the sum settles to a finite number. This is not a trick. It is a core method. Series like these help us describe waves, heat flow, and signals. Physics meets infinity in other ways. Some theories produce quantities that diverge to infinity unless we adjust the way we count contributions at very small or very large scales. The method called renormalization tames these infinities to connect equations with measured results. When this is done correctly, predictions match experiments with high accuracy. The lesson is practical. Infinity can appear in our math, while the world gives finite readings. The math must be arranged to reflect how nature behaves, not the other way around. Infinity also reaches into geometry. Draw a line. It has no endpoints. Extend it in both directions, and you never stop. In Euclidean geometry, parallel lines never meet, even if they run side by side forever. In projective geometry, used in art and design, we treat parallel lines as meeting at infinity to make sense of perspective. Both choices are useful, each for its own purpose. In cosmology, the shape of space can be open and infinite, or closed and finite, depending on the average curvature and energy content. Measurements of the cosmic microwave background suggest space is very close to flat on large scales. A truly flat universe would be infinite in extent. A nearly flat but closed universe could be finite yet very large. In both cases, what we can observe is limited by the age of the universe and the speed of light. So our observable universe is a finite region, even if the full space is unbounded. Time raises similar questions. Could time extend without end? For our daily lives, the answer has no impact. For physics, the heat-death scenario is one picture. As the universe expands and energy spreads out, stars burn out, black holes evaporate, and activity thins. That future is measured in time so long that the words hardly help. The point is simple. The equations allow a timeline that does not stop, even if events grow sparse. Again, infinity is not a shape you see. It is an open-ended process. Many common worries clear up once we separate language from mechanism. Zeno's room paradox does not block walking. Modern calculus shows how an infinite sum of shrinking times can add up to a finite total. Achilles can pass the tortoise because the times form a series that converges. The step-by-step analysis uses infinite division, but the physics of motion respects limits. What felt like a trap becomes a lesson in how to handle processes that do not have a built-in stop. The number line still holds more surprises. Between any two distinct real numbers, there are infinitely many more real numbers. That density is part of what makes the continuum larger than the whole numbers. At the same time, the set of real numbers between 0 and 1 has the same size as the full real line from negative infinity to positive infinity. A simple stretch and fold mapping shows a one-to-one match. This is another case where infinite size ignores our first intuition. Remove or compress a chunk, and the cardinality can stay the same. Infinity shows up in probability as well. If you pick a real number at random between 0 and 1, the chance of hitting any single exact number, like 1/3, is 0, yet the chance of landing somewhere in the interval is 100%. Zero probability does not always mean impossible. It can mean so thin that it does not carry weight in a continuum. This kind of thinking can feel odd, but it matches how continuous quantities behave. Computer science touches infinity through the idea of unending processes. An algorithm can, in principle, run forever, like a loop that never halts. The halting problem shows there is no general method that can decide for every possible program and input whether the program will stop. This is another limit, not of the universe, but of what formal systems can settle. It rhymes with the way infinity stretches beyond complete lists. Even in daily measurement, we meet soft versions of infinity. A camera sensor records a finite number of pixels. A sound file uses a finite number of samples per second. Yet the physical world can vary in ways that are not captured at that resolution. When we increase resolution, we approach the underlying signal. We do not reach an infinite sample, but we work with limits to get better approximations. The method is the same one used in calculus and physics. Approach a value by refining the steps. All of this draws a picture that is calm rather than dramatic. Infinity is not a monster at the edge of thought. It is a group of ideas that help us describe processes that do not stop, sets that do not end, and limits that define precise values. It asks for careful rules. It rewards that care with clean results. Countable and uncountable sets, convergent series, limits, and careful handling of endless procedures. These are the tools that keep the work steady. The earliest puzzles still teach. Halving a distance forever does not block arrival if the total time converges. A tortoise's head start does not prevent a faster runner from passing. A hotel with infinite rooms can be full and still make space. Fractions can be listed, but the real numbers cannot. Lines can run without end. Space might be unbounded even while the part we can see stays finite. None of this is wild once the rules are clear. It becomes a quiet framework for thinking about size, motion, time, and number, and it begins with the simple habit of counting. Every time someone asks what comes after the biggest number, they are already touching the endless. Infinity is not far away at the edge of the cosmos. It lives inside one more. From numbers, the question slips naturally into time. It carries lives forward with a steady pull, quiet and firm. It may be the most puzzling dimension we know. It slips past without effort and does not stop, leaving memories behind and opening room for what has not yet happened. When people first wondered about infinity, they turned to time. Could the past stretch back without a first moment? Could the future run on without a last one? These questions press on what infinity means for physics and for how we think about existence. Many early cultures pictured time as a cycle, the return of seasons, the daily arc of the sun, and the rise and fall of families suggested a wheel that keeps turning. In Indian thought, vast ages called yugas measure creation and destruction in repeating spans beyond normal counting. Some Greek thinkers spoke of eternal return, where events repeat again and again. In that view, the future is not new, but a replay of what has already been. Philosophers then asked about the chain of causes. If every event has a cause, and each cause has an earlier cause, does the chain stretch back forever? Some said it must. Others argued that a chain with no first link makes no sense, so time must have a beginning. Aristotle leaned toward time without a start, holding that something cannot come from nothing. Later, theologians in the West argued that time began at a definite moment when the universe was created. Modern science added data to the debate. In the 20th century, observations pointed to a beginning of our observable history, the Big Bang. About 13.8 billion years ago, the universe expanded from a very hot, very dense state. This was not an explosion inside empty space. It was space itself expanding, and with it, time taking shape. In this picture, asking what happened before the Big Bang may not be a useful question, because time, as we measure it, starts there. Yet, the discussion is not closed. Some models suggest a bounce, a universe that contracts, reaches an extreme, and expands again, with cycles that may repeat without end. Other ideas propose eternal inflation, where space keeps inflating in some regions, while pockets stop inflating and form bubble universes. If that is right, our history sits inside a larger process that could be unending. The future carries its own forms of infinity. If expansion continues forever, time will keep going. Stars will exhaust their fuel, galaxies will drift apart, energy will spread out. The result, called heat death, is a cold, thin state where not much changes. It is an endless timeline with little activity. A different outcome is possible if dark energy, the driver of the universe's speed up, changes over time. In a big rip, the expansion could accelerate so strongly that galaxies, stars, planets, and even atoms are pulled apart. That would be a sharp ending rather than an infinite future. Our lives reflect these large questions on a smaller scale. To a person, time feels like an arrow from birth to death. On the scale of cultures, the line looks longer. People come and go, yet the story continues. We each live through a finite stretch, and we still ask whether the river has a source or a mouth. The idea of recurrence adds a different lens. Inspired by Greek thought, Friedrich Nietzsche asked us to imagine living the same life over and over, every detail repeating. This is not a scientific claim. It is a way to test how we value our choices. Infinity here is a mirror for perspective. Physics raises other puzzles. If time were truly infinite, events with tiny chances might still occur somewhere, sometime, in an endless timeline. Even very rare arrangements of matter could appear. There could be regions that look like ours, with histories that nearly match, including people almost like us, changed only by small details. This image is hard to hold and brings problems in how we define probability and meaning across an unbounded span. It serves as a reminder. When dealing with the infinite, we must set careful rules for counting and comparing. What we can measure remains limited. We live inside time and cannot step outside to look at its whole shape. Clocks move forward, memory looks back. The rest is out of reach. Scientists build models and test them against observation. Philosophers check the logic of ideas. The limits are real, but they do not make the work empty. Time, whether it began or has always been, frames motion and change. Without it, processes have no order, and life has no sequence. The question of its extent adds weight rather than taking value away. Even when we consider time as a topic for science, it also remains a strong theme for thought. If the universe has a start and an end, we can still imagine what lies beyond those bookends. That act of imagining does not prove anything. It shows a habit of mind that tries to push limits. Time and infinity are both scientific subjects and steady grounds for reflection. They remind us that brief lives fit inside a larger pattern that may be finite or infinite, but is in any case far larger than a human span. The sky brings us back to space itself. On a clear night, the question is simple and old. Does it end? Are the stars spread across an endless field? Or does the universe have a total size? Both options challenge intuition. Infinite space means that in every direction the path keeps going, with no walls and no edge. A finite but unbounded space is also possible. The surface of a sphere is the usual guide here. On that surface, you can walk forever without stepping off an edge. Yet the surface has a finite area. In 3 dimensions, a space can be finite, yet without a boundary. To sort the question, we have to separate what exists from what we can see. The observable universe is the region from which light has had time to reach us since the Big Bang. Because light moves at a finite speed and the universe has a finite age, there is a horizon to our view. Today, that radius is about 46 billion light years in every direction. This number is larger than 13.8 billion because space has been expanding while light travels. The key point is simple. What we observe is limited by time and light, not by what actually exists. Beyond our horizon, there is likely more universe. How much more is not yet known. The sphere we can see is like a balcony view. Beyond the railing, the structure continues. Geometry gives a language for these shapes. In general relativity, mass and energy decide how space bends, and there are 3 broad cases. With positive curvature, space is the 3-dimensional analog of a sphere. Travel far enough in one direction, and, in principle, you return to your start. It is finite, but unbounded. No edge, yet limited volume. With negative curvature, space is saddle-shaped and spreads without limit, suggesting an infinite universe. With zero curvature, space is flat on large scales and extends without end, meaning Euclidean rules work well across the cosmos. Each option leaves measurable fingerprints in the light from the early universe, in how galaxies cluster, and in how gravity bends the paths of distant beams. Those fingerprints are clearest in the cosmic microwave background, the faint afterglow of the Big Bang. It fills space like a cool bath, and tiny temperature ripples carry geometry information. By mapping those ripples, scientists infer the curvature of space and current data point strongly toward flatness, within a small margin of error. Flatness does not prove infinity, but it fits either an infinite universe or a finite one so large that any curve is too slight for present tools to see. The door remains open to other shapes. Space could still be finite, yet vast beyond reach. A finite but unbounded universe is hard to picture because we are used to edges. Think about the surface of Earth. It has a fixed area, yet you can walk in one direction without meeting a wall. Replace that 2-dimensional surface with 3-dimensional space, and you get the idea of a cosmos that loops without borders. Travel straight long enough, and you could, in principle, return to your starting point. The trip would be far beyond any practical time. Even light has not had long enough to complete such a loop since the Big Bang. The expansion of space adds another layer. Distant regions move away because space grows between them. This does not break relativity because nothing outruns light through space. Instead, space itself stretches. The effect is a horizon. Some regions recede so fast due to the growth of space that their light can never reach us now or in the future. No amount of waiting will help. Those places are outside our communication zone forever. If infinity lies out there, We will not confirm it directly. We live inside a finite bubble of visibility, surrounded by the unobserved. Space could also have a more exotic topology. It might wrap in ways that create repeats, like a three-dimensional video game world where going out one side brings you back from the other. In a space like that, light from a single galaxy could circle around and arrive from different directions, making multiple images of the same object in the sky. Astronomers have searched the microwave background and galaxy maps for repeating patterns that would reveal such wrapping. So far, the sky does not show clear copies within the scales we can probe. If a wrap exists, it is larger than our current horizon. An actually infinite universe raises deep questions. In an endless expanse, every allowed arrangement of matter would occur somewhere. That would include regions almost identical to ours, down to close copies of Earth and people, and also regions very different. This is not a fantasy added on top. It follows from combining infinity with a finite set of local arrangements. Still, this idea creates real problems with probability. If there are infinitely many versions of an event, how do we compare more likely and less likely across the whole? Physicists debate whether to allow actual infinities in fundamental theories or to find formulations that avoid them. A finite universe brings its own strangeness. If space is like the surface of a sphere, there is no outside in the usual sense. Asking what lies beyond is like asking what is north of the North Pole. The question dissolves into the definition. Either way, the sky keeps us humble. The part we can study is large but limited. The pattern of ancient light hints at curvature. The spread of galaxies traces the underlying shape. We may never reach certainty about infinity, but better data can close in on the options. Wondering is not empty here. It guides measurement. A century ago, the standard view was simpler. Many scientists thought the universe was static, with stars and nebulae fixed in place on the largest scales. That picture broke in the 1,920 seconds. Edwin Hubble measured the light from distant galaxies and found they are receding from us. The farther the galaxy, the faster the recession. The pattern was not one-sided. It held in every direction. The natural reading is that space itself is expanding. The past must have been tighter. Run the story backwards, and you arrive at a hot, dense beginning. This is what we call the Big Bang. It is not an explosion in empty space. It is the growth of space everywhere, like raisins carried apart as dough rises. Any observer, wherever they stand, sees distant galaxies moving away for the same reason. Expansion alone did not explain everything. The universe is remarkably uniform in temperature across regions that seem never to have been in contact with one another if we use simple expansion. To address this, theorists proposed inflation. In the first tiny fraction of a second, space may have expanded extremely fast, far faster than light can travel through space. That does not move objects through space at superluminal speeds. It stretches space itself. Regions that were once close enough to share conditions were driven far apart. Inflation smooths the cosmos on large scales and also takes quantum fluctuations, tiny random wiggles, and stretches them into seeds for galaxies and clusters. When scientists map the microwave background, they see a pattern that matches this picture quite well. Nearly flat geometry, high uniformity, and small variations with the right statistical shape to grow into the structures we see. As with many useful ideas, inflation brings new questions. When we write down models carefully, inflation need not end everywhere at the same time. It can stop in some regions while continuing in others. This gives eternal inflation. Where inflation ends, a bubble universe like ours forms and evolves. Elsewhere, inflation keeps going, making more bubbles. Each bubble could, in principle, have different details of physics, depending on how the field driving inflation settles. Our observable patch becomes one of many. The collection is often called a multiverse. The multiverse is a bold extension. It is not added for drama. It falls out of some inflation models and from certain ideas in high-energy theory. Still, it is controversial. We cannot, with current methods, observe other bubbles directly. Some researchers argue that untestable branches are not helpful. Others point out that even if we cannot visit those regions, we might detect indirect signs such as specific imprints from a past bubble collision or patterns in the distribution of fluctuations. The discussion is active. What most agree on is that inflation, with or without eternity, gives a solid framework for why the universe looks so smooth and flat and why structure exists. While these debates continue, observations uncovered another surprise. In the late 1990 seconds, two teams studying distant supernovae found that the expansion is speeding up. Galaxies are not just moving apart. The rate at which they separate increases with time. The driver of this acceleration is called dark energy. It acts like a pressure built into space that pushes on large scales. We do not yet know its nature. The simplest model treats it as a constant energy density of the vacuum. More complex ideas allow it to change over time. What matters for the long view is that as long as acceleration continues, more and more galaxies will cross our horizon and fade from view. The observable region shrinks in content even as the whole expands. Local groups stay bound by gravity, but the wider web thins from our perspective. Taken together, these pieces form a quiet but large picture. The afterglow of the Big Bang acts as a backlight that reveals the geometry of space. The pattern is close to flat. Space may be infinite or so big that any curve hides behind the limits of measurement. Topology could be simple or wrapped in a way too large to leave repeated marks within our horizon. Expansion is real and long-running. It began hot and dense, smoothed by an early burst, and seeded with small variations that later became galaxies. The expansion is now accelerating, likely due to dark energy, and that trend defines our future view of the sky. In an infinite cosmos, duplicates and near duplicates would exist not by fate, but because endless space allows every allowed arrangement to occur. In a finite but unbounded cosmos, a straight path could, in principle, bring you back home without crossing an edge, though no photon has had time to complete the loop. In both pictures, what we can test sits inside an observable sphere set by light travel time and cosmic expansion. We rely on careful maps, tiny temperature ripples, galaxy redshifts, and the bright clocks of supernovae. Small clues lead to large conclusions. None of these ideas ask for drama. They ask for patience. Measure the patterns in ancient light. Compare them with models. Check for repeated shapes. Track how supernovae dim with distance. Use many methods to cross-check curvature and growth. Each step narrows the range. The result is a steady view, rather than a final verdict. Space could be infinite or finite, and vast. Inflation could be brief or never-ending. Dark energy could be constant or evolving. The work is to keep refining what the sky allows us to know, and that same discipline leads naturally to the strongest tests of gravity. Black holes sit where our ideas about size and limit meet real objects in space. They begin with gravity, the same pull that keeps you on the ground and the moon in its path. When a massive star runs out of fuel, pressure falls and gravity wins. The core collapses. If the mass is high enough, the collapse does not stop at a dense star. It goes further and forms a black hole, an object so compact that not even light can climb away. General relativity describes this with clear rules. Matter curves space and time. Pack matter tighter, and the curves grow steeper. Push the math to the extreme, and you meet a singularity, a place where density and curvature go to infinity. At that point, our equations stop giving sensible answers. This does not prove nature contains a literal point of infinite density. Many physicists see the singularity as a warning that the theory has been taken beyond its range. Relativity covers the large and the strong. Quantum mechanics covers the small and the jittery. Inside a black hole, both extremes matter, so a single combined theory is needed. Around every black hole is the event horizon, a one-way boundary. Cross it, and every path leads inward. Light cannot escape, and neither can matter. From outside, the horizon looks like a dark sphere that masks the interior. Time behaves differently near it. A clock falling toward the horizon runs slow when compared with a clock far away. To a distant observer, the falling clock appears to crawl and fade. In its own frame, it falls through quickly. These two views do not contradict each other. They are both correct within relativity. Black holes come in sizes. Stellar black holes weigh a few to tens of suns. Supermassive black holes sit in galaxy centers with masses of millions to billions of suns. They are not passive. Their gravity guides orbits, stirs gas, and, when fed, can power bright disks that shine in X-rays. Some drive narrow jets that run for thousands of light years. We cannot see a horizon directly with ordinary light, but we can map its shadow and the hot material nearby. The Event Horizon Telescope has imaged rings of emission around the supermassive black holes in M87 and in our own Milky Way, in line with relativity's predictions. Black holes also announce themselves when they merge. The collisions send out gravitational waves, ripples in space-time that detectors on Earth can measure. Each signal traces the masses and spins of the holes, and the moment they become one, the singularity at the center remains hidden. Relativity predicts it. Quantum ideas suggest a softer story. In loop quantum gravity, space and time may have a smallest unit. If so, collapse might avoid an actual point of infinite density and instead reach a highest possible curvature, then change behavior. In string theory, the basic objects are extended strings and branes, rather than point particles. Structure at that scale could replace the point and spread the stress. We do not yet have experimental access to those depths. What we do have is a strong set of tests outside the horizon, and their relativity continues to pass. Black holes are not necessarily permanent. Quantum effects near the horizon allow a slow leak of energy, known as Hawking radiation. In simple terms, quantum fields near the horizon fluctuate. One part of a fluctuation can fall in while the other escapes. Over very long times, the hole loses mass. For stellar and supermassive holes, the timescales are far beyond the current age of the universe. For tiny hypothetical holes, evaporation would be faster. Whether the full evaporation story is consistent with how information works in quantum theory is an open question. The information paradox asks if details about matter that fell in are truly lost. Work on quantum gravity, holography, and the statistical view of black hole entropy aims to show how information is preserved in subtle correlations even when the classical picture suggests loss. The theme of infinity comes back in a different domain: quantum field theory, our framework for particle physics. Here, fields fill space. Particles are excitations of those fields. The electromagnetic field gives photons, the electron field gives electrons, and so on. When particles interact, the math adds up contributions from many possible intermediate processes, including ones involving virtual particles. Virtual does not mean imaginary. It means they are internal parts of a calculation, not detected directly. Trouble appears when we include contributions from very high energies or very short distances. Some integrals grow without bound. If taken at face value, results like an electron's self-energy can be infinite. In the middle of the 20th century, physicists developed renormalization to handle this. The approach is careful bookkeeping with physical meaning. The bare parameters in the equation's mass, charge, are not what we measure. What we measure are effective values after interactions with the quantum vacuum are included. We define the measured mass and charge at a chosen energy scale and express predictions in terms of those infinities that arise in intermediate steps are absorbed into the redefinition of the bare parameters. What remains are finite, testable predictions. This is not sweeping problems away. It is stating that observed quantities already include the effects of surrounding fields. Quantum electrodynamics, the quantum theory of light and matter, uses renormalization and matches experiments to astonishing precision, sometimes to parts in a trillion. Similar methods work in the strong and weak nuclear forces. Renormalization also tells us that theories depend on scale. At different energies, the effective strength of interactions runs. The idea of the renormalization group tracks how a theory's parameters change as we zoom in or out. This is not only a particle physics tool, it also explains patterns near phase transitions in materials. The vacuum itself brings another kind of infinity. In quantum theory, empty space is not truly empty. Even in the lowest energy state, fields fluctuate. These zero-point fluctuations give the vacuum a baseline energy. If we try to sum the energy of all possible vibration modes, the total diverges. In practice, we regulate the calculation by limiting the range of modes, a cutoff, or by pairing terms that cancel. We then match the remaining piece to observation. Here lies a major puzzle. Observations of the universe's accelerated expansion suggest space has a tiny positive energy density, often called dark energy or the cosmological constant. Simple quantum estimates of vacuum energy overshoot this value by an enormous factor. Finding a theory that explains the small observed value without fine-tuning is an open problem. Even so, vacuum fluctuations have measurable effects in limited settings. The Casimir effect, an attraction between metal plates placed very close together, arises because boundary conditions change the allowed modes of the electromagnetic field between the plates. The force is small, but has been observed. This shows that while the vacuum is not boiling over, it is not featureless either. Infinity appears again when we push a theory outside its valid range. For example, if we try to apply our current gravity theory to distances much smaller than any tested scale, we expect to run into nonsensical infinities. This is not a failure of science. It is a guide. It tells us where a better framework is needed. The hope is a theory that merges the smooth geometry of relativity with the discrete, probabilistic nature of quantum fields. Candidates exist, but they need clear tests. These threads connect back to black holes. Near a horizon, quantum fields live on curved spacetime. The interplay gives Hawking radiation and ties entropy to horizon area. In holographic ideas, the information in a volume can be encoded on a boundary surface with 1 bit of information per tiny area unit. This link between area and information shows up in black hole thermodynamics and may hint at a deeper structure in which spacetime itself emerges from quantum relationships. If so, the infinities in classical curvature would be replaced by a finite informational density at the deepest level. On the observational side, black holes continue to guide us. X-ray telescopes watch hot disks feed central holes, radio arrays map jets and magnetic fields. Gravitational wave detectors count mergers and measure how fast the merged hole settles down. Each dataset checks relativity in strong gravity and tests models of matter under intense conditions. None of these measurements looks inside a horizon, but together they fence off possibilities and refine what any future theory must match. It is helpful to keep the language steady. A singularity in our equations signals the breakdown of the model. Renormalization replaces raw divergences with measured quantities at defined scales. Zero-point energy is a real effect in bounded systems, but its role in cosmic acceleration is not yet settled. Hawking radiation is a robust theoretical result for quantum fields on classical curved backgrounds, but a full quantum gravity description of evaporation and information flow is still in progress. These are not contradictions. They are steps that mark where our current tools work and where new tools are required. Black holes and quantum fields show two faces of the same need. At the largest densities and the smallest scales, infinities in the math point to missing pieces in the theory. At the same time, controlled uses of the infinite limits, series, renormalization, produce precise results that match what we measure. The task is to hold both facts in view while we collect better data and build cleaner models. That balance between what breaks and what still works sets the stage for a second, quieter tool that tracks change without blowing up: entropy. Entropy gives a calm way to talk about order and change. It counts how many microscopic arrangements sit behind the same macroscopic look. A tidy deck has few microstates. A shuffled deck has enormously many. The second law says that, for a closed system, the count of accessible arrangements grows or stays the same. That is why the arrow of time points the way it does. Shards do not jump back into a glass, because the number of ways for shards to be scattered is unimaginably larger than the number of ways for the pieces to be a perfect cup. Ludwig Boltzmann linked entropy to probability. He wrote a simple rule: higher entropy means the system is more probable, because more microstates fit the same large-scale description. Temperature becomes a measure of how energy spreads among those microstates. This is not about a single molecule doing the right dance. It is about the crowd. Given enough particles and enough time, the crowd explores the states available to it, and we are overwhelmingly likely to find it in regions of state space that have a massive volume. Those are the high entropy ones. Two classic challenges test this picture. The Loschmidt paradox points out that microscopic laws look time reversible. If we flip every velocity, the equations run backward just fine. So why does entropy rise? The answer leans on typicality and on how we describe systems. We do not track every particle. We use coarse-grained variables like temperature and pressure. Under coarse graining, almost all microstates that match a low entropy description will, when left alone, evolve into microstates that match a higher entropy one. The reverse set exists in principle, but is so sparse that we never see it. The Poincaré recurrence suggests that an isolated system will, after a very long time, return close to its initial state. For anything macroscopic, those times are so huge that they exceed any meaningful span. In practice, the second law wins. Entropy also appears when we mix and measure. The Gibbs paradox asks why mixing two gases of the same kind does not raise entropy the way mixing different gases does. Counting microstates correctly, treating identical particles as indistinguishable, fixes the paradox. Maxwell's demon imagines a tiny being that opens and closes a door between two chambers to let fast molecules go one way and slow molecules the other, seemingly lowering entropy without cost. The resolution comes from information. To sort molecules, the demon must gather, store, and erase data. Erasing information has a thermodynamic cost. When you account for the demon's memory, the second law holds. Information and entropy meet in a striking place: black holes. When matter falls into a black hole, the horizon area grows. Bekenstein and Hawking showed that a black hole has an entropy proportional to its horizon area, not its volume. The constant of proportionality involves the Planck length squared, tying together gravity, quantum theory, and thermodynamics. Hawking also found that black holes have a temperature and radiate slowly. These links hint that space-time might have an underlying informational structure, with bits living on surfaces that bound regions. The holographic idea grows from this. The content of a volume could be encoded on its boundary. If so, the universe limits how much information can fit into a region, and some naive infinities are replaced by finite counts. On cosmic scales, entropy tracks the history of structure. Early on, the universe was hot, dense, and remarkably uniform. That smoothness is actually a low entropy state for gravity, because gravity favors clumping. As time goes on, matter gathers into stars and galaxies. Stars burn fuel and radiate heat to space. Black holes grow, radiation thins. The total entropy rises. In many models, the universe heads toward a heat-death state. Energy spread thin, temperature nearly even, little free energy left to drive complex processes. That future could be an endless, quiet timeline if expansion continues. Entropy gives the arrow. Expansion sets the stage. Why did the universe start in such a low entropy state? That question is central to the arrow of time. The past hypothesis is a simple statement: initial conditions were special. With that assumption, the second law follows for almost all later evolutions. We do not yet know why the initial state had that character. Inflation helps explain the evenness of the early universe and seed structure, but it does not, by itself, remove the need for special starting conditions. Here, infinity enters the discussion again. In an eternally inflating picture, there are infinitely many patches with different histories. Counting and comparing outcomes across an infinite set demands a careful measure. Without it, probabilities become ambiguous. Fluctuations add another twist. In an infinite future with rare but inevitable random departures from equilibrium, you could imagine a small region fluctuating into a lower entropy state. Boltzmann once suggested our observed order might be such a fluctuation. Pushed to the extreme, this creates the Boltzmann brain problem. In a vast eternity, it would be far more probable for a single self-aware brain to arise briefly from a fluctuation than for an entire low-entropy universe like ours to form. Because we do not observe ourselves as isolated momentary brains, theories that produce this outcome as their dominant prediction look suspect. This is another case where infinity in time forces us to sharpen what we mean by typical. In daily life, entropy shows up in quieter ways. Hot coffee cools as heat spreads into the room. Fragrance diffuses through air. Batteries discharge unless maintained. We manage entropy with flows. Refrigerators move heat from cold places to warm ones by doing work. Engines turn temperature differences into motion. Life maintains low internal entropy by taking in energy and dumping waste heat. None of this violates the second law. It uses open systems and gradients to build local order while increasing the entropy of the surroundings. At small scales, thermal fluctuations sometimes make the improbable happen briefly. A tiny cluster can spontaneously adopt a more ordered configuration for a moment. Non-equilibrium statistical mechanics quantifies such events with fluctuation theorems, which relate the odds of entropy going down in a short run to the odds of it going up. As systems grow larger or times grow longer, the usual arrow dominates again. Entropy connects to coding and communication. Claude Shannon defined an entropy for messages, a measure of uncertainty or information content. The more unpredictable a source, the higher its Shannon entropy. The mathematics lines up with thermodynamic entropy, though the interpretations differ. In physics, entropy counts microstates. In information theory, it counts possible messages or compressibility. The shared structure lets us borrow insights. Error-correcting codes fight noise the way low-temperature phases fight disorder. Data compression resembles packing many microstates into fewer labels. These bridges make the abstract more practical. The theme returns to our earlier encounters with infinity. In the vacuum energy story, subtracting two formal infinities gave a finite Casimir force. In renormalization, redefining measured quantities absorbed divergences and left predictions that match reality. In black hole physics, an area-based entropy hints at finite counts beneath smooth geometry. With entropy and the arrow of time, infinity appears in the form of unbounded state spaces and very long durations. Each time, the useful move is to state the domain, set the scales, and define the rules for counting. Infinity is not erased. It is domesticated into limits, measures, and coarse grainings that let us compute and compare. There is also a human scale to this. We live far from equilibrium. The sun bathes Earth in low entropy radiation. Earth radiates back higher entropy infrared light. That difference powers weather, oceans, and life. Our machines ride those gradients, from photosynthesis to turbines. The second law does not forbid structure, it explains it. Order forms and persists where there are steady flows that export entropy. When the flows stop, structures fade. This pattern holds in cells, cities, and stars. As with black holes and quantum fields, careful language helps. Entropy is not disorder in a casual sense. A crystal at absolute zero is ordered and has minimal entropy, but a whirlpool can show structure while still representing a high entropy macrostate for the water molecules. The arrow of time is not imposed by a cosmic metronome. It emerges from statistics given special initial conditions. Reversing a movie looks wrong because the set of microstates that would make the reverse plausible is too tiny to matter. Place these ideas next to gravity again. Where gravity is strong, high entropy can look like clumps. A cold hydrogen cloud drifting in space has lower gravitational entropy than the same mass arranged into stars and black holes. As collapse proceeds, radiation carries away entropy, horizons grow, and store it. The universe can see its entropy rise while forming islands of intense structure. That is why cosmic history allows galaxies, planets, weather, and thought, all within a law that points toward equilibrium. If a deepest theory replaces smooth space-time with discrete elements, the accounting will change in detail, but not in spirit. There will still be counts of configurations, still arrows tied to typical evolution, still constraints on what information can fit where. If reality stays continuous all the way down, calculus and fields will keep their central role, and we will continue to rely on limits and measures to keep infinity in line. Either way, entropy remains the guide for direction, feasibility, and scale. The path from a shattered glass to black hole horizons might seem long, but the same principle threads through. Count how many ways things can be arranged without changing what you see from a distance. Track how those counts evolve when left alone. Use that to define an arrow. Where infinities intrude, set clear rules for how to compare like with like. That approach turns impossible questions into steady work and makes the largest mysteries manageable enough to study. Stretch the second law over an endless timeline and a limit appears. Entropy cannot rise forever without approaching a ceiling. That ceiling is the heat death, a state where energy is spread so evenly that no useful differences remain. Stars exhaust their fuel, galaxies dim, and temperatures level out. Nothing drives currents or chemistry. Change slows to a thin whisper, not because energy is gone, but because no gradients remain to do work. The timescales are far beyond ordinary reckoning. Suns live for billions of years. Supermassive black holes outlast them by factors that dwarf language. Through Hawking radiation, even the largest will eventually evaporate, but only after times on the order of 10, 100 years or more. Past that, the universe thins and cools, while expansion carries matter apart, pushing entropy toward its maximum. Infinity twists this picture in subtle ways. Given unbounded time, events with tiny odds can still happen. A rare fluctuation can create brief pockets of order in an otherwise featureless bath. The Boltzmann brane is the stark example, a random thermal fluctuation assembling for a heartbeat. A self-aware brain with memories that were never lived. The idea sounds absurd, but the math does not rule it out in an eternal, high-entropy world. That raises a test of consistency. If such brains are overwhelmingly more common than entire low-entropy histories like ours, why do we find ourselves in a long-lived cosmos with galaxies and fossils rather than in a momentary hallucination? Many physicists take this as a sign that our cosmology must avoid making Boltzmann branes typical, or else we have misapplied probability in an infinite setting. Recurrence is another implication of infinity. In a finite system that runs forever, states eventually return near where they started. Shuffle a deck long enough, and the original order reappears. If the universe has a finite number of accessible states but infinite time, it could, in principle, revisit configurations close to those of today. The arrow of time would still point forward locally, entropy would rise between recurrences, but the scenery could loop on unimaginable intervals. That picture depends on details: the size of state space, the nature of expansion, and whether new degrees of freedom keep opening. It shows how entropy and infinity entangle logic with scale. The low entropy of the early universe is a central puzzle. The Big Bang was not only hot and dense, it was unusually ordered compared with now. Uniform matter and radiation fill space in that picture, and for gravity, uniformity is a special, low entropy arrangement. As gravity works, clumps form, stars ignite, and black holes grow, all while the total entropy climbs. One view, the past hypothesis, simply states that initial conditions were special. Another view places our observable region in a much larger structure and treats our low entropy start as a rare patch within an enormous whole. Infinity offers room for rarity, but a good theory needs more than room. It needs a rule that makes our observations typical within its measure. Even with a long, quiet future, entropy carries a kind of spare beauty. It sets direction for processes, underwrites memory, and links histories together. The same rule that keeps shattered glasses from reassembling also powers stars and weather by rewarding flows from high to low. Across human spans, entropy's rise explains why fires burn one way and why engines require fuel. Across cosmic spans, it drives the large trend toward equilibrium, while allowing, for a while, islands of complexity to form and persist. Infinity returns to the equations with a sharper edge when we talk about energy. In physics, infinities often signal that a model has left its valid range. Nature does not present us with infinite energy. The conservation of energy, first law of thermodynamics, says total energy in a closed system stays constant as it changes form. Drop a weight, and gravitational potential becomes motion. Apply brakes, and motion becomes heat. Introduce an infinite amount, and the bookkeeping fails. No finite system can accommodate a boundless deposit. The math floods the page. The physics disappears. Perpetual motion schemes are the classic casualties. Machines that run forever without fuel, or that output more energy than they take in, would need a loophole in the first or second law. For centuries, clever designs promised to beat the ledger. Wheels that shift their own weights to keep turning, magnet arrays that chase themselves around. None work. The first law forbids energy from appearing out of nowhere. The second law forbids perfectly lossless cycles. Some energy always disperses as heat. These are not engineering limits that better materials will solve. They are structural rules of nature. Quantum mechanics adds texture but no escape. The vacuum is not empty in the classical sense. Fields fluctuate, and virtual particles flicker in calculations. Zero-point energy is real enough to have effects in bounded setups, but it is not a reservoir that can be tapped at will. To extract work from vacuum fluctuations, you must impose order boundaries, timing, information, and paying for that order consumes at least as much as you could gain. No free energy emerges from background jitters. The accounting still closes. Still, infinities appear in our math. In quantum field theory, summing over all possible high-energy contributions in a naive way yields divergent answers, as though the vacuum carried infinite energy density. Renormalization reframes the problem. The parameters we observe, mass, charge, already include the dressing from interactions with the vacuum. By defining those parameters at a reference scale and relating predictions at other scales through the renormalization group, we absorb the formal infinities into redefinitions and keep only finite, testable differences. This is not cosmetic. It reflects the scale dependence of physics and has produced predictions verified to extraordinary precision. Classical models had their own infinities. Treating the electron as a point with all its charge at a location makes its electric field blow up as you approach that point, implying infinite self-energy. Quantum theory replaces sharp points with wave functions spread in space, reducing the sharpness of the divergence. But a full resolution demands a deeper picture, either a structure at very small scales or a unification that changes the rules. The same lesson shows up in cosmology. Extrapolating general relativity back to the earliest instant yields a singularity of infinite density and temperature. The sensible reading is that our current theory cannot describe that regime. A quantum theory of gravity must take over where both quantum mechanics and relativity matter equally. As a thought exercise, imagine a world where infinite energy were possible. Conservation would fail. Any system could be driven to any state without cost. The notion of temperature would lose meaning because you could equalize or reverse gradients at will. Engines could be perfectly efficient. Disorder could be undone for free. In such a world, the hierarchy of processes that builds complexity, steady flows, exploiting differences, would have no foundation. Paradoxically, infinity would erase the very structures it tempts us to imagine, because distinctions that make structure possible would not hold. The role of infinity in physics is therefore double. As a tool, it helps define limits, integrals, and series that converge to precise values. As a warning, it marks the edge of a theory's map. Entropy and the arrow of time show how to keep the tool and heed the warning. You set the domain of validity, define how to count states, and track what happens under coarse graining. When the numbers threaten to diverge, you look for the scale where new physics must enter. When time tends towards sameness, you look for the gradients that still drive change and quantify how long they last. The method keeps the work honest, even when the subjects heat death. Boltzmann brains, singularities, lean toward the extreme. Across these topics, no miracle shortcuts appear. Gradients, power structure, structure exports entropy. Laws conserve energy. Fluctuations exist, but do not grant free engines. Where infinities intrude, we use careful definitions or we look for better theories. The quiet thread is that scales matter, counting matters, and limits matter. Within those boundaries, the largest and the smallest can be described in ways that stay finite, predictive, and connected to what we can observe. The idea of every event happens somewhere needs care. An infinite stage does not mean every script is performed. It means that if the rules allow a configuration, then given enough room, that configuration can appear many times. This is the simplest multiverse picture, one universe of continuous space that extends without bound, sliced into far-flung regions beyond one another's horizons. Those regions are not other worlds in a mystical sense. They are ordinary space, too distant to ever meet us. If matter arrangements repeat across such a stage, it is because the number of local patterns is finite, while the stage is not. The copy of you, if it exists, is not connected by a tunnel or a hidden door. It is separated by distances so large that light could not bridge them even in far longer than the age of our universe. A second family of ideas comes from inflation. Early rapid expansion can end in patches, making bubbles that cool, form particles, and evolve into universes like ours. Elsewhere, inflation continues and spawns more bubbles. Each bubble is a region with its own cosmic history, and possibly with slightly different values for basic quantities. The phrase, eternal inflation, describes this open-ended birth of pockets. We only see the interior of our pocket. Other pockets are behind horizons that are not just far away, they are causally disconnected. In this multiverse, repetition is not required by infinity alone. Variety can arise because the mechanisms that end inflation may settle into different outcomes in different places. A third route appears in quantum mechanics. The many worlds view says the wave function that describes a system never collapses. Instead, when outcomes that cannot coexist are measured, the combined state branches into non-interacting components, each with a different result. In this sense, there is a branching structure of outcomes for any quantum process. These branches are not far regions of space. They are separate components of the full quantum state. You cannot travel between them or send signals across them. The idea removes randomness from the laws by moving it into which branch an observer finds themselves on. The cost is accepting that reality includes all the branches. These pictures are different. An infinite space multiverse repeats patterns across distance. An inflationary multiverse creates many cosmic pockets over time. A quantum multiverse branches outcomes within a single mathematical state. People sometimes merge them in casual talk, but the mechanisms and the kinds of other versions they imply are not the same. Keeping the types separate helps with clear questions. What could, even in principle, be observed? What depends on initial conditions? What depends on the form of quantum theory? Tests are hard. We cannot fly to another bubble. We might, however, look for scars. A collision between two inflationary bubbles, if it happened in our past light cone, could leave a circular imprint in the cosmic microwave background. Searches have not found a confirmed signal, but they set limits on how often such collisions could have occurred. We can also test inflation itself by measuring patterns in ancient light, the distribution of galaxies, and the possible presence of a specific swirl signature called primordial B-mode polarization. The more tightly inflation is pinned down, the more we can say about whether eternal versions of it are plausible. Probability is the deep difficulty. In a multiverse with infinitely many regions, how do we define the fraction of regions with a given property? This is the measure problem. Counting by raw number fails, because both the numerator and denominator are infinite. Using cutoffs in time or space can bias the answer. Different reasonable measures can give different predictions for what a typical observer should see. Without a stable measure, statements like, "Most universes are X," do not carry clear meaning. This is not a minor technicality. It is central to turning the multiverse from a picture into a tool for making quantitative claims. Another theme often linked to the multiverse is the anthropic principle. In its weak form, it says, our observations are conditioned by the fact that we exist. We should not be surprised to measure laws and constants compatible with life, because we are only able to measure from a place where life can arise. In a multiverse where constants vary across pockets, some values would allow chemistry, stars, and long-lived structures. Others would not. If there are many pockets, it is not odd to find ourselves in one of the rare, life-friendly regions. This line of thought can feel unsatisfying because it does not derive numbers from first principles. Used carefully, it is a filter. It rules out claims that would make intelligent observers effectively impossible, and it highlights which ranges of parameters are compatible with structure. Closer to home, there is a different repetition that does not require infinite space or exotic branching: topology. If the large-scale shape of space wraps around like a three-dimensional torus, a photon leaving in one direction could, given enough time, return from the other side. The sky would hold repeating patterns if the wrap were small enough compared with our horizon. Observations have looked for such repeats and have not found them within current limits. That pushes any wrap, if it exists, beyond the scale we can see. but it shows how a finite space can still mimic certain kinds of repetition without invoking unreachable regions. The multiverse can also be confused with the simulation idea, the claim that reality is a computer program running elsewhere. One is a physical proposal about space, inflation, and quantum law. The other is a philosophical speculation about substrate. They answer different questions. Physics can ask what signals a bubble collision would leave. It cannot, with current tools, distinguish a perfectly faithful simulation from a base reality, because identical physical predictions would follow from identical rules. Why keep such big pictures on the table if evidence is scarce? Because they arise naturally from theories that do have evidence. Inflation explains several features of the observable universe with quantitative success. Certain models of inflation almost inevitably produce many bubbles. Quantum theory predicts interference and entanglement that match experiment across countless tests. The many worlds view preserves that mathematical structure without adding collapse rules. Infinite space follows if measurements of curvature keep pointing to flatness, and if the topology is simple, each step is anchored to work we can check. The extensions are bold, but not arbitrary. Care with language helps. Another you in an infinite space multiverse is not a twin with whom you could ever interact. It is a distant arrangement of atoms that matches your arrangement inside some huge region. In many worlds, another you refers to a component of the quantum state that evolves separately after decoherence. In inflationary pockets, another you could only exist if the local physics of that pocket permits biology similar to ours. Each phrase uses you for convenience. None implies identity in any strict sense. The pull of these ideas can be strong, so it is useful to recall what does not change. The methods remain the same. Define a model, derive predictions that differ from alternatives, and compare with data. If two models give the same predictions for everything within reach, they are empirically indistinguishable at present. That is not failure, it is a boundary. As measurements sharpen, boundaries can move. Better maps of the cosmic microwave background, larger surveys of galaxies, and improved gravitational wave observations all tighten the range of viable early universe models. In particle physics, learning more about neutrinos, dark matter, or possible deviations from the standard model could feed back into which inflation mechanisms are favored, even without a final verdict. The multiverse debate clarifies tools we need in any case: how to reason in the presence of very large numbers, how to define typicality, how to separate selection effects from dynamical laws. It also reminds us that infinity changes how probability feels. An event with tiny local odds can become common across unbounded space or unending time. That does not make every fantasy inevitable. It says that what the rules allow and how often it appears depend on both dynamics and scale. There is a quieter lesson too. Our observable universe is finite. Its age and the speed of light define a horizon. Everything we know with data sits inside that sphere. All larger pictures must reduce to the same physics within that boundary. The success of that local physics, how well gravity, quantum theory, and thermodynamics describe what we see, sets a standard any broad claim must meet. A multiverse that explains why our constants permit galaxies but contradicts observed patterns in ancient light would not survive. A theory that keeps all local successes and adds careful, testable edges earns its place in the conversation. The question that opened this path: does infinite space force every history lands in a measured spot? Infinity expands what is possible. It does not decide what is real. Mechanisms decide. If space is unbounded and roughly uniform on the largest scales, then arrangements will repeat somewhere beyond any hope of contact. If inflation is eternal, then distinct cosmic pockets with varied details may exist, separated forever. If quantum mechanics is universal and unitary, branching occurs within the wave function. Each statement follows from a different if, and each if points to observations that can sharpen or soften its weight. We often use tools we do not fully grasp. People drove cars long before most drivers understood combustion. Sailors crossed oceans without a map of the globe. In the same way, we use infinity through rules and symbols without holding it in the mind like an image. That is not a flaw. It is a sign that thinking can reach beyond what it can picture. Mathematics gives a careful path. Define how a process grows without end. Set limits that capture the outcome, and check the result against reality. When the checks work, we keep the rule. When they fail, we revise it. Infinity is handled, not hugged. Computers show this split between use and understanding in a sharp way. A machine is finite. It stores a limited number of bits and runs for a limited time. Yet it can model processes that, in pure math, extend without bound. It does this by approximation. A series that would need infinitely many terms is cut after a point where the error is smaller than we care about. A curve that needs infinite detail is sampled at a high rate. The model improves as we increase steps, memory, or time, but it never becomes exact in the mathematical sense. Still, planes fly, bridges hold, and images render. The method is practical. Approach the infinite by improving the finite. That approach also keeps us honest. When people say something is infinitely complex or infinitely unlikely, they often mean too large to count or too small to matter. Physics replaces such phrases with scales. We ask how precision changes with more data, how error shrinks with better resolution, how a signal stands above noise. Where a simple model breaks, we add details. Where adding details brings no gain, we stop. Infinity becomes a direction to move in, not a claim about what the world contains. Language adapts. In everyday talk, infinity is a way to point at awe. In careful work, it is a way to point at process. Consider a coastline. Up close, it has bays and rocks and spray. Measure with a long ruler and you miss the small twists. Use a shorter ruler and the length grows. In pure math, a curve can have fractal detail at every scale, so the measured length diverges as the ruler shrinks. Real coasts end at grains of sand. The lesson is not that nature is infinite. It is that scale matters, and models must state their scale. Vision science gives another angle. The eye sees a limited range of light. The brain fills gaps with guesses based on past scenes. We do not store every pixel. We store compressed hints. A sunrise feels wide and endless, but what we hold are edges, colors, and a sense of space built from cues. Something similar happens when we face very large or very small numbers. We form a sense of much bigger or much smaller and stop trying to picture exact amounts. Infinity pushes that habit to its limit. We replace pictures with rules. Education wraps that shift into steps. First, we count. Then we learn that counting does not stop. Then we learn to add fractions that seem to go on forever and yet sum to a tidy number. Finally, we see how going on forever can be handled by limits that give precise answers. Each step lowers the need for raw imagination. and raises the need for careful definitions. The mind still wonders, but it also measures. Art and music turn this into feeling. A canon that repeats a theme again and again feels endless and calm. A circle in a painting, with small circles nested inside, suggests an order that might keep going. A poem can loop a line, so the end meets the start. These are finite works that hint at the infinite by pattern. They work because the brain likes closure, and also likes the tease of something that could continue. Infinity becomes a flavor rather than a fact. Ethics even touches the theme. When choices affect very large numbers of beings or very long spans, our usual sense of scale bends. Decisions about climate, species loss, or long-lived waste reach far beyond one life. No one can feel the weight of millions of years, but we can still reason about trends and limits. Here, too, we replace pictures with models, and we test models with data. Infinity is not a target for morality, but it is a backdrop that asks for humility. History shows how this humility keeps progress steady. Early calculus worked with infinitely small steps that critics mocked as ghosts. Limits made the method clean, and physics bloomed. Early electrodynamics produced divergent self-energies. Renormalization and the scale dependence of couplings turned that mess into predictions with 12 decimal accuracy. Early cosmology hit singularities. New ideas, like inflation and quantum corrections, reframed what the equations could say. Each time, the infinite was tamed by better framing, not by a grand denial or a leap of faith. The same pattern holds when we move between discrete and continuous pictures. In traffic flow, we can track each car or treat the stream as a fluid with a density and speed. Both views can be useful. At low density, car by car matters. At high density, waves of slowdowns move like ripples. We choose the model that fits the scale. Infinity seems to lurk when we try to mix levels without care, expecting a smooth curve to describe a crowd made of steps, or expecting a sum of steps to produce smoothness without enough averaging. The fix is to state the level and respect it. Probability and the way it changes in huge spaces calls for the same care. In small samples, rare events might not appear at all. In large samples, they appear with predictable frequency. In unbounded samples, some events with non-zero chance become certain to appear somewhere. That shift can trick intuition. We guard against the trick by naming the ensemble, the measure, and the question. Are we asking about time in one place, about space at one time, or about many trials across both? Infinity changes answers by changing which ensemble is relevant. There is also the question of meaning. If everything allowed by the rules occurs somewhere in a vast setting, does that drain value from any one path? The human answer circles back to scale. We live in finite bodies with finite time. Our choices matter in that frame. The presence or absence of distant copies has no effect on the next word we say, the help we give, or the harm we avoid. Physics can stretch the frame to cosmic size. Ethics and meaning work where we stand. The sciences thrive when this division of labor is clear. We use infinity to sharpen math, to define clean limits, to model processes that approach but never reach extremes. We avoid treating infinity as a physical stockpile of energy or a card to play when a theory stumbles. When it appears as a divergence, we ask whether a new scale enters or a different description is needed. When it appears as an endless count, we ask how to define fractions of an infinite whole in a stable way. Where counting or energy would blow up, we check the domain. Practice reinforces the point. Engineers build feedback systems that keep processors within safe bounds. Astronomers design surveys that sample the sky in a way that avoids bias. Statisticians set priors and stop rules so that inference behaves well in large data limits. Computer scientists prove that some problems cannot be decided in finite time and build tools to handle the undecidable by approximation. Every field has its version of respect the limit. Even in daily life, we use the same pattern. We do not plan forever. We plan for a season, a year, a lifetime. Savings grow with compound interest that tends toward a limit as rates and times change. Exercise builds strength in small steps that plateau, not in sudden leaps without bound. Learning adds layers that accumulate over long spans, but always with rest and revision. The brain, the body, and the world are finite. Working well with them is about steady limits, not endless surges. There is room, too, for quiet wonder that does not demand belief in literal infinities. Stand under a dark sky, and the star field feels boundless, even though our view has a horizon. Watch a tide roll in, and the rhythm seems endless, even though each wave ends. Read a sequence of numbers that converges and feel the pull toward a value, even though the steps never cease. The sense of the infinite can be present as a mood that helps us relax into scale rather than fight it. The story we have followed numbers without end, space that may not close, time that may not stop, singularities that signal theory limits, quanta that tame divergences, entropy that sets an arrow, and multiverse pictures that stretch possibility shows a pattern. Infinity is not a monster to slay or a prize to seize. It is a boundary concept that asks for care. When used with limits, measures, and scales, it yields clarity and power. When taken as a literal substance, it invites confusion. This is why the sideways 8 on a page is both modest and deep. It is a sign to proceed with definitions. It is a reminder to ask what is being held fixed, while something else grows without bound. It is also an invitation to keep curiosity open. Questions about what lies beyond what we can see, or below what we can test, are not mistakes. They are the engine of new work, as long as they come with the next question: what can be checked here and now? In that spirit, the idea of the infinite can live side by side with the practice of the finite. We can think about limits that never end, while working with numbers that do. We can model a heat death billions of years away while tuning an instrument for tonight's sky. We can consider branches of outcomes in quantum theory, while counting actual clicks in a detector. The balance is the point. It keeps the mind wide and the work grounded. So we keep the tools that make infinity useful series, limits, measures, asymptotics, and keep the warnings that make it safe domains, scales, cutoffs, coarse graining. We let art and metaphor carry the rest, not as proofs, but as ways to live with ideas larger than pictures. The result is not a final answer about the endless. It is a way to keep asking sound questions in a world that sometimes feels boundless and sometimes shows its edges. A way to let the infinite guide the finite without undoing it. It forces us to ask what we mean by fractions of an infinite whole in a universe without an overall edge. Counting how many regions have property A versus property B gives infinity in both boxes. Ratios become undefined. This is the measure problem in cosmology. To make statements like, most observers see X, you need a stable way to compare infinite sets. Different cutoffs by time, by volume, by light cone give different answers. The lesson is not that the question is pointless, but that we must choose a clear rule before talking about typical outcomes. Until then, probability in an infinite cosmos floats. Physicists handle similar issues by working with densities instead of totals. Energy density is energy per volume. Number density is count per volume. If those are finite and well-defined, the infinities of the whole space stop causing trouble. We also restrict attention to what is observable. Our horizon gives a finite sample of the universe. Within that sample, probabilities can be tied to frequencies, subject to known limits like cosmic variance, the unavoidable noise from having only one sky to measure. This restraint is not a retreat. It is a way to keep claims inside the range of what data can support. The wider pattern appears across physics. When infinities show up, we add scales and cutoffs. A cutoff is a boundary in energy or length beyond which a model does not claim to apply. Effective field theory formalizes this. It says, describe nature with the degrees of freedom that matter at a given scale, and include higher-order corrections that are small at that scale. As you move to higher energies or smaller distances, you replace the theory with another that has the right parts active. This is not hiding the infinite. It is organizing knowledge by relevance. Chemistry does not need quarks. Nuclear physics does not need strings to describe oxygen. Each level has its own clean rules until a new scale demands new ones. Renormalization is the partner of this idea. Parameters run with scale. Couplings change as we zoom. Two famous examples go opposite ways. In quantum chromodynamics, the strong force gets weaker at higher energies, a feature called asymptotic freedom. This explains why quarks behave almost freely inside high-energy collisions, even though they are confined inside protons at low energy. In quantum electrodynamics, the coupling grows slowly with energy and would diverge at an absurdly high Landau pole, far beyond any scale where the theory is meant to be trusted. Gravity might have its own safe behavior. The asymptotic safety program proposes a fixed point where gravitational couplings approach constant values at very high energy, making a predictive quantum theory without uncontrolled infinities. Whether nature follows that path is an open question, but it shows how the strategy works. Look for stable behavior as scales change. Holography sharpens the limits. A black hole's entropy is proportional to its horizon area, not its volume. This leads to bounds like the Bekenstein bound and covariant entropy bounds. There is a maximum information content that can fit inside a region before it collapses. If information is finite per area, then whatever infinity spacetime suggests at a smooth level is replaced by finite counts at the deepest level. The adds, CFT correspondence, and exact duality in certain spacetimes makes this concrete. A gravity theory in a volume is equivalent to a quantum theory on the boundary with a finite, countable set of degrees of freedom per area scale. We do not live in anti-de Sitter space, but the lesson points toward a general rule. Geometry may emerge from underlying quantum information, and apparent divergences in curvature are artifacts of missing microphysics. Black holes press the point. Singularities in classical relativity mark where the map ends. Cosmic censorship is a conjecture that such singularities are hidden behind horizons, keeping predictability safe for outside observers. The information paradox tests that safety. Hawking's calculation says black holes radiate thermally and could erase the details of what fell in, clashing with quantum theory's demand that information is preserved. Decades of work, unitarity islands, replica tricks, microstate counting in specific string setups suggest that information is not lost. It is encoded in subtle correlations, in the radiation, and in the quantum structure of spacetime near the horizon. The firewall debate asked whether that structure ruins the no-drama passage for an infalling observer. Here again, infinity lurks as a warning. Taking classical curvature to infinity, or treating quantum fields without gravity beyond their range, creates contradictions. Adding the right microstructure smooths them. Even without black holes, nature puts ceilings on how much can happen. No detector can record infinite precision. The Heisenberg uncertainty relation links spreads in position and momentum. No experiment can access infinite energy. Accelerators bend under cost and materials. No telescope sees infinite detail on the sky. Diffraction and noise set limits. These facts sound mundane, yet they are guardrails. They keep us from reading too much into the parts of equations that wander off to infinity while reminding us to phrase questions in ways experiments can answer. The practice shows up in lattice methods, where space and time are replaced by a grid with finite spacing to tame ultraviolet infinities. As the grid is refined, predictions converge toward continuum values. Lattice QCD uses this to compute hadron masses from first principles with remarkable accuracy. Dimensional regularization uses a different trick. It moves the calculation to a space with a non-integer number of dimensions, where integrals converge, extracts the finite piece, and returns to 4 dimensions. These are tools, not dodges. Each has rules that keep results consistent and testable. In cosmology, regularization looks like window functions and masks. We cannot observe the whole sky at full fidelity. Our own galaxy glows and blocks, but we can model the contamination and subtract it statistically. When we estimate the power spectrum of temperature fluctuations in the cosmic microwave background, we report uncertainties that include the fact we have only one sky. In large-scale structure, surveys cover finite volumes with complex shapes. Analysts use mock catalogs to understand how those limits bias counts. Everywhere, the same theme: define the domain, state the cutoff, correct for the window, and report the residual uncertainty. Infinity becomes a boundary condition for honest inference instead of a claim about data we do not have. The same care applies to multiverse talk. If inflation is eternal, cutoffs are unavoidable in counting pocket universes. If quantum branching is universal, you need a rule for assigning weights to branches, a Born rule, so that more frequent remains meaningful. If space is simply infinite and homogeneous, frequency becomes a question of density in a large but finite window, then a limit as the window grows. Each framework can be made precise, but none allows a quick leap from infinite to everything happens with equal weight. Weights come from dynamics. For everyday reasoning, we can keep to simpler ground. Models should earn their keep where data live. The dynamics of planets, the spectra of atoms, the cooling of a star, the lifetime of a muon, these sit far from infinities and are described with high precision. Edge cases, the first instant of expansion, the core of a black hole, the ultimate fate of the vacuum, remain open because they mix scales in ways our current tools cannot unify. That is not failure. It is a to-do list that points to where better theories will matter most. There is also a caution about language. Calling something infinitely large or infinitely small in casual speech can hide important structure. A very large number might still be finite in a way that makes a process slow but possible. A very small scale might still be big compared with the Planck length. Saying a series goes to infinity might mean it diverges so slowly that for all practical purposes it behaves like a constant over the range we care about. Good practice is to replace such phrases with concrete scales. How many orders of magnitude? How many E-folds? How many sigma past the mean? When we do need to reason about the infinite directly, mathematics gives safe routes. Limits define what it means to approach a value as steps go on. Convergence tests tell us when infinite sums settle to a number. Compactness and completeness tell us when sequences have accumulation points. Measure theory defines almost everywhere, so that sets of measure zero events with probability zero in a continuum can be ignored in averages without being declared impossible. These tools are dry only in form. In substance, they are the rails that keep thought from slipping when the ground is too wide to see its edges. On the human side, the pull of the endless should not be mistaken for a license to claim more than we can know. It is healthy to imagine other cosmic domains, other branches, other eras. It is also healthy to return to the lab bench, the detector readout, and the sky map. The balance is where science stays strong. Infinity then becomes a direction for curiosity rather than a destination. It tells us where the edges of maps lie and where new maps are needed. Set beside all this, the mind's dance with the endless is not wasted motion. It keeps generating better questions. Why are the initial conditions low in entropy? How does information survive black hole evaporation? Does gravity have a safe, high-energy fixed point? Is there a natural, small value for vacuum energy that avoids empty infinities and fits observed acceleration? Each question is a refinement punched out by earlier tangles with divergence. Each has testable edges, improved polarization maps of the microwave background, sharper black hole images, better timing of gravitational wave events, tighter lab bounds on short-range gravity, more precise measurements of expansion history. We return then to a simple stance. Work where data hold, mark where theory bends, add scales where claims blow up, and treat infinity as a limit in math and a warning in models. The universe does not hand out bottomless energy, endless precision, or infinite counts we can observe. It does hand out patterns that persist, laws that link scales, and clues that point past our current reach. Following those clues with restraint is how we learn from the places where equations run to the edge. How do you talk about likely when both an event and its alternatives happen without limit? In eternal inflation, where bubble universes keep forming, that question becomes hard to ignore. This is the measure problem. To make any prediction, you must count outcomes. But when every box on the shelf holds an infinity, ratios lose meaning. Different counting rules give different answers. Until a stable rule is found, some statements about what most observers see float without weight. Infinity does not just widen possibilities, it blurs them. Physicists distrust infinities for reasons like this. It is not a dislike of large numbers. It is that an infinity in a calculation usually means the method was pushed past its range. A map of a city can be precise. Extend its streets into the sea, and the lines stop matching terrain. In physics, the fix is rarely to accept the ocean as a street. The fix is to redraw the map with the right coastline. That redraw has several candidates. String theory softens point-like interactions by spreading them into tiny loops of vibration. When collisions are smeared across length, fields do not spike into singular peaks as easily. The worst divergences ease. Loop quantum gravity takes a different route, building space from discrete units of area and volume at the Planck scale. When geometry is granular, curvature and energy density cannot blow up without limit. They top out at finite values. Other ideas look for asymptotic safety, a fixed point that tames gravity's behavior at very high energy. Each approach aims for the same outcome. Keep the successes we already have, remove the places where the math breaks, and make new predictions testable at the edges of observation. Hints show up in special cases. Some models of black holes replace the singularity with a finite core or a bounce, where quantum pressure halts collapse before density becomes ill-defined. Early universe scenarios try to smooth the Big Bang into a transitional phase that connects to something before, again avoiding a true infinity. None of these proposals are settled, but they share a lesson. When infinities arise, it is often because two good theories, quantum mechanics and general relativity, are being used in a regime where neither alone is enough. A better joint frame is needed. Even far from those extremes, infinity asks practical questions. Quantum field theory predicts a huge vacuum energy if you sum over all modes naively. The observed value tied to cosmic acceleration is tiny by comparison. The gap is so enormous that it is often called the worst prediction in physics. Most researchers read this not as evidence that space brims with hidden power, but as a sign that our counting is wrong. We are missing structure. A future theory will need to explain why the vacuum acts almost empty, and why its small leftover pushes the expansion the way it does. Infinity also erodes clarity if left unchecked in logic. If everything happens somewhere, careless reasoning can prove almost anything. That is not science. To keep explanation meaningful, we need weights that do not depend on arbitrary cutoffs, and we need links from those weights to things we can measure. Patterns in the microwave background, statistics of galaxy maps, timing of gravitational waves, spectra of high-energy particles. Where infinities tempt us into empty claims, the cure is to demand concrete signals. This discipline shows up in effective theories. The idea is simple. Do not demand a single equation that covers every scale. At each scale, keep only the parts that matter there. Let parameters run with energy and match neighboring descriptions in their overlap. Chemistry does not need quarks to predict a reaction. It needs the right potentials and thermal statistics. Nuclear physics does not need strings to describe carbon-1,2. It needs nucleon forces calibrated to data. At very high energies, the description must change again. No one part pretends to be final. The chain is strong because each link is honest about its range. When infinities appear within a valid range, we have tools. Regularization reshapes the calculation, so intermediate steps are finite. Renormalization replaces bare parameters with measured ones and tracks how predictions shift with scale. Lattice methods cut space into a grid, then refine the grid until results settle. Dimensional tricks shift the calculation to spaces where integrals converge, then pull out the finite piece. These are not cheats. They are ways to keep the connection between symbols and experiments tight. On the gravity side, information bounds change the conversation about how much. A black hole's entropy scales with area, not volume. That points to a deeper rule. The number of independent degrees of freedom in a region may be limited by its boundary. Holographic dualities show this in certain spacetimes with mathematical precision. If a boundary can encode a bulk exactly, then apparent infinities in the bulk are really artifacts of using a smooth description beyond where it counts bits correctly. The cure is not to declare the bulk unreal. It is to recognize that bulk geometry emerges from something more basic. Back at cosmology's frontier, the measure problem remains, but the path forward looks familiar. First, list the assumptions: eternal inflation or not, constant dark energy or changing, simple topology or wrapped space. Next, pick a clear measure and show how it links to observables. Then test. If two measures make the same predictions in our sky, they are indistinguishable for now. If they differ, better data will choose between them. In the meantime, working with densities instead of totals, energy per volume, events per horizon patch keeps arguments grounded. Amid all this, it helps to recall what is not in dispute. The expansion is real. The early universe was hot, dense, and smooth. On large scales, with tiny seeded ripples, gravity curves space. Quantum fields fluctuate. Entropy grows, giving time its practical arrow. Black holes merge and ring down in ways that match general relativity. Light curves around mass. Atomic spectra match quantum rules. None of these rely on actual infinities. Their precision comes from models that respect limits and scales. This does not shrink the topic, it sharpens it. Infinity keeps returning as a boundary concept. It appears when we divide without end, when we sum without cutoff, when we follow geodesics backward to a point where our map folds. It is a warning that we have reached a place where definitions must be made exact or replaced. It is also a tool for clean thought. Define a limit, ask what value a process approaches, and keep the conditions clear. Used this way, infinity gives calculus its teeth, statistical mechanics its averages, and wave theory its spectra. There is also a sober ethic that grows out of this view. Do not claim that infinity delivers free energy or perfect prediction. It does not. It marks the need for care. Do not patch over a divergence with rhetoric. Fix it with a better model or admit the range has ended. Do not treat the multiverse as a license to assume anything. Tie it to mechanisms, to measures, to potential signals. Do not assume that a singularity is a real place. Treat it as a signpost that says, new physics required. The search for that new physics is not vague. It has targets. Improve maps of the cosmic microwave background, especially its polarization. Watch more black hole mergers and compare their ringdowns to strong field predictions. Time pulsars to probe gravitational waves with galaxy-scale baselines. Build better atom interferometers and short-range tests to look for deviations from Newton's law. Hunt for dark matter with multiple methods. Measure the expansion history with independent tracers. Each step narrows how wild the infinite can be at the edges, or forces us to redraw the edges themselves. Infinity also stays close to us in quieter ways, in number lines that never stop, in series that settle to a sum, in limits that define smooth motion, in the way error shrinks as samples grow. It is present whenever we say, keep refining and watch a result stabilize. It appears in the way we compress a huge world into a small model and then expand the model's reach by increasing resolution. It is in the habit of asking what happens as time becomes long, as steps become small, as data become many. For human meaning, the lesson is steady. We do not need literal infinities to feel scale. The night sky already puts us in our place. The spans of geologic time already slow the pulse. The smallness of atoms already humbles. Knowing that our maps have edges does not make the land smaller. It makes the path clearer. Accepting that some questions sit at the boundary does not empty them. It turns them into guides. So the picture that remains is practical and wide. Infinity is not a substance to be found. It is not a warehouse of energy or a promise that every fantasy is realized. It is a sign on the road, sometimes a tool in the kit, sometimes a red light that stops us from driving off the pier. It enters when we let a process go on without bound in thought, so we can extract a clean number. It flags where a theory needs help. It loosens the grip of small pictures and keeps curiosity from closing early. The mind will keep circling it. Children will still ask about the biggest number. Students will still watch 1, 2, plus 1, 4, plus 1, 8 creep toward 1 and feel the tug of a limit. Engineers will still design for tolerances that shrink as models improve. Astronomers will still look for signs that space bends or wraps on scales beyond today's view. Physicists will still wrestle with vacuums that seem too empty and horizons that seem too informative. Writers will still use infinity to talk about love, grief, or hope, when ordinary words run short. Through all that work and wonder, a simple rule holds. State the scale, name the limit, mark the domain. When infinities appear, either use them carefully as mathematical limits, or treat them as warnings to look for a better frame. Keep the parts that predict and test them hard. Let the rest wait until evidence and clarity catch up. That way, the endless does not swallow meaning. It sharpens it. The subject began with a question about what has no end. Along the way, we met endless numbers, unbounded space, arrows of time, black hole horizons, vacuum riddles, and branching possibilities. Each time, infinity pressed us to define more carefully, to measure more precisely, and to imagine more widely without drifting free of ground. That is its gift. It stretches the mind and tightens the method at once. If a deeper theory finally arrives, one that joins gravity and quantum rules without singular spikes, one that explains why the vacuum is nearly empty, one that fixes how to weigh outcomes in an unbounded setting, it will likely treat infinity with respect, not as a literal thing, but as a limit that organizes thought. It will keep the parts of our current picture that work and retire the parts that break. It will move some horizons back and bring others into view. Until then, the path is clear enough. Work within the scales we can test. Push those scales outward, step by step. Use infinity where it makes calculations clean, and pause where it makes reality vanish. Let wonder do its work, without letting it write the answers. The night sky will go on being large. Numbers will go on being without end. Questions will go on asking for more light. And as the light comes in faint, patient, measured, we will keep walking by it, quietly, as the horizon keeps drawing away.